All right, so this is ES204. Dynamic. Okay, so let me give a quick, let's talk about dynamics. So what do you think dynamics stands for? What do you expect to learn in this class? Okay, so basically, perfect. So basically is the study of the motion. So there's two ways to study the motion. Okay, so one here, yeah, dynamics. There's two ways to study the motion. One that you have probably done in physics is by using, you probably don't remember the equation, the name of the equations, but I'm going to call them kinematics equations. But the equations, you're going to know exactly what are those two equations. So let's see. A equals to what? Derivative of time with respect to the derivative of velocity with respect to time, dv dt. I'm sure it's not new, no? Now, what will be v? Correct. Derivative of the deformation of the position with respect to time. So this is the first way to study the kinematics. And this is generally what is known as particle kinematics, okay? Or study of the motion of the particle. Because you assume that particle has no mass. So we're going to do that the first, I think, week, okay? The first two lectures, I think that's what we do. More than that. For first part of the semester, that's what we do. We just focus on kinematics. But there's another way to study the motion of an object, which is what? It's the one that is known as kinetics, or which is the same as dynamics. But this time, what would be the equation that will be used? Summation of forces equals to ma. So Newton's second law, no? Okay. So I'm going to put really only that one, but just for this case, I'm also going to put summation of moments equals to I alpha. Okay, so since we're going to study the motion, let's say the motion of an object, we can break it into two different components. So for example, this marker can be moving. Right, so this would be rotation. We could move it in translation, or it could be a combination of both, no? So basically, we know that the motion of any object, we can always move it into some type of component that will be due to translation, plus rotation. Okay, and I'm probably going to repeat this a lot. Okay, once we move really to kinematics, probably after the first two lectures, we really move deep into kinematics. And we're going to go. So for example, here for translation rotation, here I'm just going to put it as an orientation. If we use the kinetics equation, in general, the summation of forces equals to ma will define the translational motion. And what would be the equation defining the rotational motion? Summation of the moments. So if you think about structures, if you go to solid mechanics or the classes, generally, the summation of forces would define, if you want, bending, and the summation of moments will define torsion, no? Okay, so think about that way. You can also break what's happening in a structure by knowing if it's deflecting or translation, or if it's twisting or rotating, no? It's the same approach, okay? Okay, so I'm going to do a quick review over here. quick review of basically these two equations over here that you see over here. So basically we say that the motion you can have translation, or rotation. So the cases you have studied is for translation. Generally, you assume linear acceleration A equal to constant, but what would be the equivalent for rotation? Would be angular acceleration to be equal to constant. Okay, for structure will be torque, correct. So for this, so basically A here, I think you'll know is if you want, I mean, let's just say, yeah, linear acceleration. And alpha is what? Angular acceleration. Okay, so I'm going to rederive the equation that you should be familiar with. For the translation, they will be identical for the rotation, so we'll do that very quick. And then what is going to be new in this class is that the acceleration, in most cases in real life, they don't have to be constant. Yeah, so for example, let's say you have, even with your car, okay? What happened at the beginning? If you start accelerating with a car, what is the first source of the friction? I mean, hopefully you're not sliding too much, no, in your car. But basically it would be the friction of the tires with the road. But as you start increasing, so the first force that's impeding you to move is the friction of your tires with the ground, no? Then as you start going faster, which one will become the main force that try to stop you? The air, the aerodynamics, no? So you can say that the acceleration in one case would depend on the position, depending on what type of road you are, and they might depend on the velocity because it would depend on the velocity of the wind, no? Okay, so if you assume constant acceleration, so on, that will run into problems. So how will you derive these similar equations that we're going to derive now if you have cases where the acceleration is not constant? Okay, but first let's do the simple case where A is constant. Okay, so let's see, if we start from here, let's start first by the translation. And all this should be a review. So let's say we start by the equation A equals to dv dt. So we're trying to solve for V. So what do? We do separation of variables. A dt equals to dv. So let's say here we integrate. So A is constant. So if you want, I can put it outside the integral. Let's say integrate between 0 and t. And this between V initial and V final. So if I integrate this, what do I get? AT equal V final minus V initial. Or we get V final equal to V initial plus AT. Okay. Oh, something that I maybe did not mention. I know some professors check the attendance. I think you're adults, and the reason I don't check attendance is because if we spend, let's say, 2-3 minutes every single class checking attendance, if you multiply that by, what do you say, 14 weeks, it will be 28 times. You will be missing over one lecture, no? I'd rather spend that time covering material, okay? So we have this, now let's try, so now that we found the velocity, let's see if we can find the position. So the other equation we have is V equal ds dt. So this will gives you V dt equal to ds. But here, what is V? V is V initial plus AT that we just calculated dt equal ds. So let's say we integrate this between initial point, final point, and then in order to simplify this, we integrate this between 0 and t. So if we do this, what do we get? D initial times t plus what will be the integral of AT? One half AT squared will be equal to S final minus S initial. Yes. I can try, but then remind me to move the page up and down because I do whatever I do. Is that better? Yeah. So now from here you have, for example, let's say the final position should be equal to what? Initial position plus V initial t plus 1/2 AT squared. Okay, so I hope, I mean, you don't have to, but I hope that you kind of remember a little bit these equations from physics, no? All right. Then I'm going to cover a third one that generally is the one that gives you a hard time, but it's simple algebra. It's basically, generally you have the velocity, the position, and then you have another one that gives you the velocity in function of the acceleration of the position. Okay, so let's see what would be that equation. And okay, so for this one, there's two ways to do it. Okay, so let's say we have A equals dv dt and V equal ds dt. So in here, let's say, let's assume that the time constant is eliminated, okay? So what I would say is two things. So let's say we need to find a relation between these two, eliminating the time constant. So these two ways to do it, okay? The first one, I think is the most logical. It's not the one I use to tell the truth, but I think is the most logical. Let's say you write here dt for the first equation will give you what? What would be dt? dv over a, no? Now, if you do the same thing with the other one, what would that give you? ds over v. So now here, if you only look at these two equations, now we find a relation that is v dv equal to ads. Okay, does that make sense? You want to eliminate the constant time, you equate the two equations to the constant time, so you can eliminate it, no? I think that's the most logical, if you ask me. So you can do this, or the other method, which is generally the one I use just because it's a little bit faster, and I'm used to it, but doesn't mean, personally, I don't think it's better. I think this one's more logical. The chain rule. So if you use the chain rule, let's say we know A equals dv dt. I can rewrite this as what? dv ds times what? ds dt, no? Okay, what is ds dt? So in other words, this will give you what? A equals dv ds times v, or this could be again v dv equal to a ds. Yes, you can see you can use either one, no? I think this one is just a bit faster, that's why but you can use either one. Okay, so now let's say, so using, let's say v dv equal a ds. And now let's say, remember a is constant, so we can put it outside the integration sign, or if you want to keep it inside between s initial, s final, and let the say would be v initial, v final. So this would be equal to what? What will be the integral of v? V squared over 2, no? 1/2 of v squared, so we have 1/2 of v final square minus v initial square. And this would be equal to what? A final minus s initial. So this will give you what? V final square equal to v initial square plus 2a s final minus s initial. That this one in many books you just call it d as the distance. And probably you remember this equation as well from particle dynamics, no? Or not, okay? But basically the other expressions were what? In function of time, no? Velocity in function of time, position in function of time. This one is the one that gives you the velocity in function of position, if you want, no? Okay. Okay, so we did that for the translation. If we do this exactly the same thing for the actuation, so following analytical procedure for rotation, sorry. We're still going to do it, but let's say. So what is the expression for the, what is the equivalent to A equal dv dt for rotation? Alpha equal to what? Okay, we say A equals to alpha. V is the velocity, T is the time. So this will be what? D omega dt, where what is omega here? Angular velocity, but basically it's the same, no? Same structure. So now, for example, this one, if we separate the variables, what do we get? Alpha dt equals to d omega. So we follow exactly the same procedure as before. What did we do before? If you look at this one, we have A equals dv dt. We do v initial, v final, 0 and t, no? We do exactly the same thing. We take here between 0 and t, and here we're going to take what? Between initial angular velocity and final angular velocity. So this should give you what? Alpha t equal to omega final minus omega initial. We will give you that the final angular velocity is equal to the initial angular velocity plus alpha t. This equation has letter different than this one, no? Yeah, the only thing, this one is related to translation, this one is related to rotation. Okay, so now we're going to do exactly the same thing on the second step. Okay, so look at the second step, what we did. We're going to do exactly the same thing. So the next step, we're looking exactly at what I did here. What do we have? So we call this one. So the next, the relation, what is the relation of, what would be the equivalent to V? What would be the equivalent to V equal ds dt? When you have something moving in rotation, this time we're not talking about the distance that is changing, but what? The angle. So we know that angular velocity will be equal to what? D theta dt. Good. So now we can rewrite from this one, omega dt equals to d theta. But what is omega? We just calculated, no? So it's, I think I used the blue before, so omega initial plus alpha t dt equals to d theta. And we're going to integrate this between what and what? This will be between 0 and t. And this will be between initial and final. So we're going to get omega initial t plus what? 1/2 of alpha t squared will be equal to omega final minus omega initial. So if you compare this one to the position, we have S final equal to what? S initial. So here we have initial angle plus omega it plus alpha t squared over 2. Nothing really different than what we did before for the position, no? So one describes the translation, the one describes the rotation. Okay, and finally, if you want, let's do the same thing as we did with the other one. So I'm just going to do one this time. So, okay, which one do you want to use of these two methods? You want to rewrite this in function of dt, or you want to use the chain rule? This one, the first one? Okay. So basically that way we don't do it both ways. So here again, we have the two equations will be what? Alpha equals to d omega dt. And we know that omega equals d theta dt. I agree with you. I think this one is more intuitive than the other one, okay? So if you want to eliminate the constant time between both of them, what you can do is rewrite dt will be equal to d omega divided by alpha. And the other one will give you what? D theta over omega. Now, because alpha is constant, what can you do now? How is this called in differential equation? You do separation of variables, no? Correct? You do separation of variables. Now that you have done separation of variables, you are allowed to do what? Integrate. So again, this is going to give you alpha omega final minus omega initial will be equal to 1/2 omega final squared minus omega initial squared. And this equation should be very similar to which one? If I have it here. To this one over here. So you'll see we'll have omega squared final will be equal to omega initial squared plus 2 alpha of omega final minus omega initial. Okay. All right, but let's say here, in many occasions, the accelerations, let's say A or alpha, are not constant. And can be in function of, let's say, position, time, or velocity, or other things. Okay, but this would be the main thing. Okay, so if that is the case, what would be the procedure we have to follow? So let's say here, procedure. So step one. Write kinetic equation or equations, okay? But basically here is either A equals dV dt, B equals ds dt, or if it is rotation, what would be the equation here? D omega dt, and omega equals d theta dt. Oh. Okay, so this procedure values for everything, A in function of position, velocity, or so on, okay? So you rewrite whatever they give you, and the second step will be to separate the variables in such a way that you can integrate. So separate the variables. 3 will be integrate. And 4, you will solve. I mean, really, you do the step 2, 3, and 4 like almost at the same time. But the reason, I mean, you will find out, but I'll tell you right now anyway that I do the same thing with all my courses. I'm not picking when I grade exam about the final answer. So for example, let's say the final answer, each problem for me in an exam is worth 10 points, okay? The right answer at the end is worth 1 or 2 points. What's important for me is the procedure about how you get to the answer. That's worth 8 to 9 points, okay? So if you look at it in this class, I think every single problem that I solve, I try to solve it in 4 steps on the procedure. That's what I do, 1, 2, 3, 4, okay? And that's what I'm looking when I grade exams. Okay, so if you do the correct procedure and you do a numerical error, that doesn't mean you don't know how to do the problem, no? Okay? So that's why I try to give you as many points as possible. If you do the problem correct, but I don't see any procedure, what would be my opinion? That person is very lucky, but needs to go buy a lottery, okay? Or I will ask that person, how did they do it? And I will give them a similar problem. And tell them, do it the way you just told me you did it. And guarantee you 90% of the time, they're not able to do it, okay? But because something happened in the middle, no? So we don't know what it is. But anyway, just say that the only thing I want to here insist on is that I'm very fond of procedures, okay? So follow the steps. When you do the exam, so this is something I cannot check when you do the assignments, but when I do the exams, you will see every time I follow the same steps. Yes?
Is this for kinetic or kinetic?
This is, here we are just, I mean, this is, kinematic equations. But actually, you also have 4 steps when we do kinetics. But it will not be this one. It will be do a free body diagram, write down kinetics equations, find additional equations, and solve. Okay, but yeah, good point. This is kinematics, not kinetics. Thank you. Write kinematic equations, which are these ones over here. Okay, so let's start by the first example, which is, let's look at actuation in function of position. So basically here, what I'm trying to say is that A is not constant. A will be in function of S, where we say that S is the position. I mean, you all understand that this means actuation in function of position, no? They only happen once to me, but I had a student that insists to me that this one meaning A times S. So it wasn't a good start, no, for the class, but we are clear this is A in function of S, no? Okay, all right. So if that is the case, I do it in general, okay? It's not that clear when you do a general procedure, but once you do a clear example, it becomes clear. So step 1 will be to do what? You can write A equals dV/dt. So this is the general kinetic equation. But in our case, A is not constant. What is A? Is A in function of S is equal to dV/dt. So in this case, can we separate the variables? Because what are the variables we have? Position, no? Position S, velocity, and T. If you want separate variables, what is the maximum number of variables we could have? 2, no? Yes? So here we have 3. So what does that mean? We're going to have to eliminate one of them. So how can we eliminate here, let's say dt? We could write this as what? A of S equals to what? dV ds times ds dt. What is ds dt? V, no? So now this becomes what? Acceleration of S equal V dV ds. Now, how many variables do we have of integral? We have the position S and the velocity V. So, what can we do now? We can separate the variables. So we can do step 2, no? Yeah. So step 2 will be what? Actuation of S ds will be equal to what? VdV. Now that we have only one variable on each side, so let's say here one variable. What can we do? We can go and integrate. So we can integrate here, let's say, as ds equals VdV. So let's say here, I mean, I'm gonna just to put something, you don't need to put it, but S initial, S final, V initial, V final. And finally, whatever the problem is asking you to do, what can you do? Solve, no? For whatever you need to solve, okay? But you see that this procedure should work, no? Yeah? Yes. Sort of, yeah, but you don't have to do the mathematics, yes. The idea is that you understand a procedure and you always follow the same steps so that you get to a solution. Okay, that's the idea. So we're going to do one example now. So I don't use notes for nothing except for the problem because otherwise we spend too much time. So let me find out one for this. Okay, so I found here problem 13, and this should be out of the book or out of the what?
Can we simply plug in the values in the formulas we derive?
That have nothing to do. The equation we derive is A equal what?
For the translation.
For everything. What is the assumption we made? Is that A and alpha were what? Constant. In this case, they are not constant. So that would be a big mistake. Okay. All right, but it's good. It's a good question because that way everybody makes a difference. So let's see, page 1, 2, 3, 4, 5. Okay. All right, so let's see this problem. I don't know what it is. I have here a figure, but looks like there is probably some type of rifle or something like that, or chamber. So once you buy this stuff online, this should also give you access to an ebook. So I think there's some type of bullet or projectile which is contained in some type of barrel, I'm guessing. All right. And it looks like initially this is at a distance S. And they give you that the actuation of this object is a constant divided by S, where C is a constant. And S obviously is the position, okay? So basically in here, you recognize that in this problem, the actuation is in function of the position, no? Yeah. So let's see what they give you in this problem. So let's say, looks like they give you, if you know the initial position to be 1.5 meters, the final position to be 3 meters. You know the initial velocity is at rest, so 0, and that the final velocity is 200 meters per second. Okay, what we need to find out here is to determine C, the constant. Okay, so I'm going to tell you the truth. When I look at it now, I have no idea what we need to do, but let's follow the steps, no? Okay. Step 1. We write down the kinematic equation. A equals dv dt. Okay, in our case, we know is A of S equals dv dt. And if you want, we can start putting values now, okay? I think it would be probably easier. What is our expression for A of S in this case? Is C over S equals to dv dt. C is a constant. So again, here how many variables we have? S, V, and T. We need to get rid of one of them, no? So we can get rid of T, no? By using the chain rule. So we can write over here C over S equals to dv ds dt, and we know that ds dt is V. So we can rewrite this as C over S equals to V dv ds. Now that we only have V and ds, what can we do? We can go to step 2, which is separation of variables. So we can write this as what? Let's see. C over S ds will be equal to V dv. Okay. Now that we separate the variables, what can we do? We can go and integrate. So that will be step 3. So let's say we do integral of C is a constant, no? So if you want, no, let's just do this way. Doesn't matter. CS ds equals to V dv, and we can integrate this between what and what? Between S initial, S final, B initial, B final. So to simplify this a little bit, simplify, just to make it a little bit more clear, C is a constant, so I can actually move it outside the integral sign. So we have ds over S equal B dv. So if you want, we can write the constant of integration, since I'm doing it as initial, as final, the initial, the final. But the reason why I will write this under this form is because what will be the integral over here of ds over S? What would that be? Natural log of between S initial, S final. What will be the integral of V squared of V? Correct, between V initial sorry, and V final. So I did the integration of variables here. Okay, so we're integrating. Now what do we need to do? We need to solve for C, no? Okay, so let me do next page here. You see everything is kind of continuous, but I'm going to put step 4, no? Okay, so 4, 5, 6. So let's say we have C, so step 4. we have C log of S final minus log S initial equal to 1/2 V final square minus V initial square. So I mean here, whatever you want to do is. Now we can solve here for C. So what would be C equal to? C you can say would be equal to, let's say, V final square minus V initial square divided by 2 log, oh, you can actually simplify this. Yeah, we're gonna do on the next step. I mean, you don't have to, but because this will give you the result, no? But also we also be equal to, this will be equal to what? V final square minus V initial square divided of 2 log of S final over S initial, no? Okay, so you see, to me, this is done, it's over, but in this problem, what do they ask us to do? They actually ask us to find the numerical value, no? Personally, I don't care, but I tell you right away, that's not the part that I'm testing you about how to use a calculator, but let's say here, numerical application. Basically, my goal in this class is what? Is to teach you steps 1, 2, 3, and 4, no? Okay, to do the numerical application, it's just a consequence of the problem. So let's say this will give us what? C. What do we have in this problem? What is V final? 200 square minus 0 square divided by 2 times log of S final is 3 divided by 1.5. Excuse me, and I have a result here. So the acceleration here said that this is equal to 28.85 10 to the 3. Yes. I don't understand the question, but basically what I want to say here, maybe to answer your question, is that if it wasn't an exam, what I'm interested is in up the work up to here. This is not that important. Imagine an exam, you just give me this at the end. What do you think is going to be your grade? Not that good, no? Okay, I don't answer your question. On the assignment, I don't have the control because the assignment is online, but on the exam, that's the way I look at it. Since we're talking about that on the assignment, also something I try to set up, because sometimes it's an issue, is that sometimes those stuff online are very picky about the decimal parts. I think on this one, I don't know if I did this stuff, but I think was a setting that they say that you don't need to give the result up to the second decimal, okay? You can have, let's say, 5 or 6% error that it should count to be correct, okay? But my advice would be is that if when you do the assignment, please keep 2 or 3 decimals if there is middle step calculations, or even better, use MATLAB or a computer, no? Or your calculator, since you're at home, no pressure of time or anything, so you can keep as many decimals as you can. Because sometimes you are doing the problem correctly, but the system is saying you are doing it wrong because you didn't round off somewhere in the problem, okay? So be careful with that. Okay, any question about the procedure? Yes. Yes. That was given to you. They tell you that the acceleration of the projectile here is given by C of S. Yep, no problem. Since we have 15 minutes, let's see if we have time to do another one, but this time about something different. So let's say acceleration. In function of time. So what does that mean? A equal A of t. Okay, procedure remains the same, no? Okay, let's do one example. I think this is problem 1334. You know what, we're going to change this. I think the example I have, this one is too long. So velocity. Just erase a little bit, and we put here v. And next time we do time. But v, I think this would be 1340. It doesn't matter which one. The other one, the example looks they were like 2 pages, and I don't want to rush anything. So, okay, so problem 1340 from the figure that I have looks like is actually looks like an unmanned vehicle completely. I don't know if that's the goal of the problem or not, but and this one looks like it's attached to a parachute. So actually, this is a very good example of the acceleration in function of the velocity, because what's going to happen as the velocity increases, the drag force is going to be higher and higher, no? Okay. That's what they used to use for the space shuttle when they have one for the landing, okay? Or even when they drop the stuff from space, you see the parachute opening. Okay, so in this problem, looks like they give you that the acceleration, the braking acceleration over here is equal to A equal to minus 0.004 v squared. So basically, this is the braking force, the deceleration, no? And it looks like they give you the T initial, or T1, in this case, looks like is 0. Looks like T2 is what you need to find. And you know that the initial velocity is 50 meters per second, and that V2 is 10 meters per second. So here you need to determine T2. Yeah, so this one is straightforward. That's why I think I want to do this. Okay, so what should be step 1? A equals to dVdt. In our case, A is in function of what? V, no? A V equals to dVdt. So we can write this should be equal to what? Negative 0.004 v squared equals to dVdt. You see, this one is a lot easier than the one before, because how many variables do we have now? V and T, no? So we don't need to do anything special. So we can go to step 2, which is what? Separation of variables. In this case, what I think would be easier is to do Yeah, I think that would be the easiest thing to do. Yeah. Minus 0.004 dt equals to dv over v squared. Hopefully this is the best way to do it. So now that we have separated the variables, what can we do? Can go and integrate. So let me just write this. We have negative 0.004 dt, and we're gonna have dv over v squared. So here, maybe just to give you a hint, what is the derivative of 1 over v? Okay. So maybe that should give you what is the derivative of this, no? So that means what? We're gonna have what then? This would be equal to negative 0.04. I forgot it's 0, sorry, 0.004. Negative 0.004 T2 minus T1, if you want to put here T1, T2. Final. Okay, I'm not going to do the integral right away here. So what should be the integral of over here? What should we have over here? Minus 1 over v. Between what? V1, V2. Yes? Okay. Okay, so let's see, let's do some algebra here. We can eliminate the minus sign. Let's okay, we can go, let's say, what do we need to solve for here? T2, no? And we know T1 is 0. So, okay, so let's say step 4 already, okay. We have 0.004 T2 minus 0. That would be equal to 1 over V2 minus 1 over V1. So, all right, so I can just solve over here. T2 will be equal to, I'm sure this is an easy number, but what is the inverse of 0.004? So it will be 4 divided by 10. Whatever it is. And this we have here 1 over, what do we have for V2? V2 is equal to 10 minus 1 over 50. And I think I have here a solution that this should give you T2, but you can go and check, please. To 20 seconds. And I don't know what happened. Okay, what is that telling us? I don't know what happened. I don't know what happened. Okay, is that 20 seconds? Okay, so basically next time, if you want, you can write it. What is the only one we have left is acceleration in function of, what do we do? Time, no? So next time, yeah, we did position, velocity. So next time we do the example we couldn't do before in function of time. Okay, guys. See you next week. This is not working anymore.
Acceleration is a function of S. Can we use double integration?
There is no double integration here. No, don't make it more complicated than it is. I don't know what's going on here, so